All right, we're back. And quick disclaimer, if you haven't seen the video right before, please, I encourage you to go watch, okay? It's very important. And what we do in this video is very much based on that video. And so if you recall that video, right, what we just did, we considered the case when the dimension of V is greater than the dimension of W. Okay, so the astute viewer might think, well, what the heck happens if the dimension of V is less than the dimension of W? That's what we're gonna look at right now. And you might have guessed, I just noticed I made a little mistake. This is supposed to be not injective, right? Well, what does this mean? I think even if you don't have an understanding of what's going on here, I think it's not too far to stretch to say, well, this means T is not surjective. I mean, I gave you that hint in the previous video. But it actually makes a lot of sense, and let's look at why. It's similar to why we explored in the previous video. But again, let's look at a smaller set here for V, and then a bigger set for W. So just the reverse of what we talked about in the previous video. We're looking at a linear map from V to W. Okay, well in this case, we don't have that same problem as with the previous case because, well, you can obviously fit V inside of W. In fact, you can fit a bunch of V's instead of W based on this picture. But we can't, just using V, we can't account for all of the W's, right? Because linear maps, functions in general, can only take a single point to a single point. So we can only at most take up maybe this much space in W, okay? So using that kind of intuition, this makes sense, no? Because to be surjective is to take up the entire codomain space. Okay, but we gotta prove that rigorously, right? So that's what we're gonna do. Again, using this bad boy up here, this fundamental theorem of linear maps. So let's prove that really quickly. So again, a proof, again, very simple. When it comes to surjective, remember in a previous video, we talked about looking at the range of T. If the range of T is all of W, then it's surjective. But it's an equivalence, right? So the converse is also equivalent to saying that the range of T is not all of the codomain space, W. And so what does that mean? Well, if the dimension of the range of T is strictly less than the dimension of W, right? Well, that's just saying that this list of, there's some basis of the range of T, right? That basis has to be a smaller length than the basis of W, and so it can't possibly account for everything in W. Okay, are you following? Yeah, leave a comment if any of this is confusing you. I know I'm skipping a few steps, but I'm assuming that you've watched the other parts of the series, and so a statement like this, it would follow pretty quickly that, well, range of T has to be, a proper subset of W, and therefore T is not surjective, okay? So this is what we want to show. And so let's calculate what range of T is, the dimension of range of T, using our handy-dandy theorem. Well, again, subtracting out that null of T, we have dimension of V minus dimension null of T. Okay. Well, what do we know about this, all right? If the dimension of the null space, let's check. So dimension, again, what we need to show here is that this thing, what we know, right? This is just basic arithmetic, right? Dimension of null space, I mean, dimension is always non-negative, okay? So of course, if we're subtracting this off, this is always gonna be less than or equal to, well, whatever we have that's being subtracted from, okay? So dimension of V in this case. And what did we assume? Dimension of V is strictly less than the dimension of W. Well, great. So what have we done? We've done exactly what we wanted to do. We take that far left-hand side, compare it to that far right-hand side. What's our equivalence? For our operator, it's less than, strictly less than. And that's what we wanted to show. And so that concludes that little bit. Okay. So that allows us to just check this guy off real quick. Those two theorems done. We have one more little itsy bitsy kind of fun little fact that we're going to explore in the next video too. So I'll see you then.